Okay, is the recording on? Okay, I think it is. All right. So for the remainder of today, we will cover quantum Fourier transforms and eventually quantum phase estimation, and this is based on the chapter in the K. Laflamme-Mosca book, chapter 7.1, and it's Kiskit 3.5 and 3.6. Okay, so I think the plan is sort of remind you about periodicity and Fourier transforms, then binary representations, and then we'll eventually get to circuits. You can see that I was writing the plan as I was writing the lectures. So what is periodicity? And this is not a trick question. This is sort of perhaps one of the most important, periodicity is probably one of the most important ideas in the universe. It's basically how we learn things. You know, if things don't recur, we don't know if it was could have been noise. Periodicity basically means that if there's a function, if you move a certain distance away, the function repeats itself. And of course, you can apply it recursively so that f of 2j, so r being the period, right? So f of j is equal to f of j plus r. R is called a period, and this, you know, j and r could live in one-dimensional space, in two-dimensional space, in three-dimensional space. It doesn't really matter. That's the definition. If you apply it again to f of j plus r, then you can see that f of j and f of j plus 2r is the same, and f of j plus 3r, and so on and so forth is the same. Now, this is sort of an expansion on what we already seen in the Simon's algorithm, because there was a translation by one period, right? The function was itself plus, you know, plus some string. But then if you, because it was modulus 2, if you added another string, again, you would get back to f of j, right? Whereas here, the idea is that, you know, j plus r, j plus 2r, and so on and so forth are all distinct, okay? The reason why it's so important is because one reason is because there are things that are called crystals, and that's sort of the basis of our, if you like, existence. Our technology is based on being able to create strong materials, and crystals tend to be strong. So this is my cartoon of the salt crystals. So sodium chloride molecules arrange themselves in some periodic arrangement. And the repeating pattern is called a unit cell. So in this case, I drew something that has 2 atoms per unit cell, sodium and chlorine. And these unit cells can be numbered 1, 2, 3, and so on and so forth. And so the size of the crystal is the number of periods. So it's R times, you know, very large number, because crystals tend to contain an Avogadro's numbers of a number of molecules. And the question is, since R tends to be very small, like angstroms, we can't really see it with the naked eye oftentimes. So how do we know that R exists? Now, of course, those of you, I think it's fair to say that the more sort of elementary example of a crystal, of course, is in a time domain, like when we think about frequencies, when we think about radio. The reason why we can transmit signals oftentimes is because there is a frequency at which your circuit will vibrate and emit radiation at that frequency. And so if you know what that frequency is, you can tune to that frequency. And so having this repetition, this, you know, periodicity is really kind of sort of one of the really central ideas in you know, all of science, I would say. The reason why we study harmonic oscillators is for the same reason. We should have really clear understanding of periodicity. So maybe it's not that surprising that one of the major breakthroughs in quantum computing came from understanding how periodicity works. Now, right, so now to get back to the practical question of how do we measure periodicity, and the trick is Fourier transform. And the way this is done in nature or whatever in technology is through, for example, Bragg peaks in X-ray scattering. And so the crucial sort of conceptual idea is to be able to transmute the information from real space, position space, to Fourier space. And this has all the properties of a linear transform. The information is not lost, it's just rotated. And the idea somehow is that in real space, if the particle is, for example, in this, if we're talking about this molecule or that molecule, or the third molecule, then this becomes very, very precise, right? It's here and not there. Whereas if we want to talk about periodicity, it's not a property of an individual molecule, it's a property of the structure. And the idea somehow is that the property of the structure is not encoded in any one molecule, but it's encoded in the infinite number of these molecules. And therefore, going into the, we have to change a basis in the way we represent things. Now, these are words, and this is math. So if you're given a function, f of j, which we suspect or say we know it's periodic, and the challenge is to find the period, the protocol is that we want to go away from f of j at any particular j to consider infinite sums over all j. Okay, you can compute an average of f of j. That's an example of an infinite sum. But the trick of the Fourier transform is to encode, to try to tease out information on the behavior of f of j by encoding it with this extra. Let's see if I can get the cursor here, laser pointer, perfect, right? So you can see that there are these extra phases that one hangs. And just to remind you, e to the 2 pi I is 1. Okay, does that make sense? So let me pause for a second, especially those of you who haven't seen Fourier transforms. Well, maybe I should ask first, those of you who have seen Fourier transforms, is this so far so good? You can post things in the chat, or maybe I should ask. I have a poll question. Shall we continue? Right. Yeah. Okay. I'm sorry. When I get phone calls, well, I'm not going to answer this. It's probably doctor's offices, stuff like that. Sorry, my kid wasn't feeling well this morning, so I'm expecting a phone call from the school. Yeah, so let me look at the poll. What are we? Yes, everybody's happy with this, or most people at least. Good. Right, so here's the math of the Fourier transform. We sum over all values of f of j. But of course, if we just compute an average of f of j, we'll lose information. So the idea here is that we want to add it up, but then have a parameter in there, which is this k, which is an integer, which is somehow going to try and keep track of all of the information in f of j. Now, just to remind you, e to the 2 pi I is 1. So in order for this so-called phase factor to be interesting, whatever 2 pi is multiplying here has to be less than 1, or not equal, at least not being an integer, because e to the 2 pi I, e to the 4 pi I, and so on and so forth, that's how you lose information, because they're all equal to 1. Anyway, that's the justification for, if you like, for trying to have a multiplier here that discerns different patterns of f of j by being a phase. You're basically painting a phase on numbers. Right? Each of the f of j is going to have a slightly different complex number ascribed to it. Now, here's the trick of the Fourier transform of the Bragg peak. Because you have periodicity, this infinite sum from essentially 1 to n, or from 0 to n minus 1, can be broken up into subsums, right? So the idea is that if this thing is periodic with period r, you can peel away the first r, the second r, the third r contributions. And because this thing is periodic, it will, well, okay, that's the next step. So these groups of contributions, they're unit cells. This is, if you go back to, let's see if I can go back. Right. If you go back here, you imagine that each unit cell contains, you know, r units of length. And so what we've done here is we basically separated each unit cell by itself. Now, because this thing is periodic, what you see is that you can, the value of f recurs from this subsum to that subsum to that subsum. However, the value of the exponential does not recur. And this is what I've reshaped here, that n refers to which of these subsums you're computing. And j prime, it used to be a sum over j from 0 to n minus 1, but now it's a sum of j prime from 0 to r. This is a sum within the unit cell. And you can see that which unit cell you're dealing with is now kept track of a new index, little n. Okay. Anyway, this is a mathematical sort of a trivial, what's the word? Not triviality, truism. You don't need to prove that. You just need to reshape the sum. And the terminology that you should be mindful of, because ultimately you will be reading at some point in your life literature, and you should be able to recognize the terms. The amazing thing about the Fourier transforming a periodic function is that it factorizes. So once you go into the case space, into Fourier space, it factorizes into something called a structure factor and something that's called a form factor. So this is a jargon that you most often see in X-ray scattering. But because, you know, this kind of sort of a spectroscopy is very common, you can do it with neutrons, photons. This is how we see gratings, you know, the optics, all of the optics works this way. So the structure factor has the information about the periodicity of the structure. Whereas the form factor, you can see that it actually knows about the behavior of the function within the unit cell. So this will be able to differentiate whether the solid is made of salt molecules or just pure sodium or something else. So the shape of this function, say if f was density, the shape of this function will tell you what's inside the unit cell. Whereas this thing, it has no information about the atoms themselves, except that they're positioned with a certain periodicity. Okay. And this is the only thing that we focus on here. Whereas in real life, people tend to focus on the other thing. Well, both really, but okay. Now, so having separated into a structure factor and a form factor, we want to look at the behavior of this guy. And especially in the limit where you know, you're dealing with an infinite crystal, so n over r goes to infinity. And what you see is that this has a peculiar property that as this sum goes to infinity, you know, unless r times k divided by n is an integer, this will be a sum of infinite number of random phases. So it'll most likely add up to 0. And so here's this condition. You can actually do the sum explicitly. Maybe I'll put it on the homework for you to play around and compute the sum explicitly. It's a ratio of 2 signs, and you can plot it. And it has this property. If you haven't seen it, you should definitely do it. Let me just sketch it here. And right. So this sum becomes, it's one of these sine rk and actually let me not try to almost sure to get it wrong. It's a sine over sine type object, maybe squares, and it behaves like this. It's the interference, it's the famous interference pattern. And so you get a peak if Rk over n is an integer. Now, let me ask you whether, have you seen delta functions? Should we talk about delta functions? Do you know what a delta function is?
Can we go over it again?
You don't know what a delta function is. Okay. So a delta function is a bookkeeping device that was invented. So I don't know. It was pretty. Oh, that's interesting. What does it say? You cannot minimize Zoom whilst you're recording it. That's weird. Yeah. Let me come back. Let me finish. What was it? What is it that I was going to say? Yeah. Yeah, let me come back to delta functions in a bit. Since I don't have it on my notes, I'll just have to write it freehand. The point is that there's this, the property of this S of k is that it's a very strong peak when a certain condition is satisfied, and it's practically zero otherwise. And if you have seen delta functions before, this should ring a bell. But you know, if you need a review or you need a proper refresher on that, it won't ring a bell. So let me just come back to this slide after I go through delta functions. For now, I just want to just put up the generalization of what a Fourier transform is if you're dealing with sort of hardware implementation of bits, and especially qubits. This object, which I essentially lifted from, you know, standard math notation, can be thought of as a change of bases. So, you know, I think conceptually it is a change of bases even in the classical case. But when you deal with quantum mechanics, any kind of a change of bases.
Professor,
yep.
they're not sharing.
Oh, whoops. I apologize. Well, I understand. Thanks for telling me. Why am I not sharing it? Where's my sharing pane? Come on. 1 second. I lost my sharing button. Oh, I know why. Because there we go. Okay. So what I said was that the behavior of this S of k in the limit, you know, in the limit of large n is that of a delta function. So we'll have to come back to that, and I'll have to explain what it is. And I think the best, well, okay, right. But before I do that, let me go through just the rest of this sort of a definition slide. In the same way that we think of the classical Fourier transform as a linear transformation between real space and Fourier space, you know, we can think of that transformation as a matrix. And, you know, as usual, matrix has a vector that you feed in and a vector that spits out. And so this Fourier, this pattern of phases can be thought of literally as matrix elements of this big matrix. Okay. And you can see that the inverse of this transformation, just like in the classical domain, is the same matrix with minus signs replay, you know, basically these phases being e to the minus 2 pi I. And at this point, this should start sort of ringing a bell, because what you see is that for a single qubit, if you think of, you know, n equals 2, x and y are either 0 or 1, right? And so what you see is that the usual Hadamard transform is an example of a Fourier transform, because it maps 0 to 0 plus 1 and 1 to 0 minus 1. And that's exactly what there are only two choices of this combination, either 0 or 1/2, right? And 1/2 is e to the pi I, either the 2 pi I divided by 2, so that's e to the pi I, and that's a -1. So let me not continue with this until I explain delta functions. But let me, okay. 1 second, let me create that page. Okay, let me share it. All right. So let's talk about delta functions. Okay. So the notation is delta of x. And so delta function is thought of as a very peak. So if you think of you know, functions that look like this or some other functions, delta functions look like very peaky functions. At least they're visualized this way, but that's not how they're even defined. The way delta functions are defined is through their behavior inside the integrals. Suppose you're trying to compute an integral, which is an integral of a function times the delta function of x minus x naught. Right? X minus x naught means that, you know, the interesting point is x naught. And so the definition of a delta function is that no matter what this function does elsewhere, so let's say this is f of x, multiplying it by a delta function, which is, you know, 0 elsewhere, guarantees that this integral is f of x naught. Okay? And this is it. You can ask what kind of functions behave as delta functions, and usually what we think about is that a delta function can be thought of as a limit. Let's take the example that we already saw, and then we ask ourselves, what does a Gaussian look like? Well, a Gaussian looks like this, right? So it's basically e to the minus ax squared, where the width of this is square root of a. Okay. So we now see from this that we can think of a delta function, if we like to be a limit of a Gaussian when a goes to 0. Whoops. Right. No, sorry, somebody should have stopped me. Right. Okay. But based on what we heard from Ricardo earlier this morning is that we need to, right, the important thing is that since the integral of the delta function with itself is 1, you can see that it has properties of the probability distribution. So it's a particularly peaked probability distribution. A has to be equal to, what do we say, pi over a over pi, sorry, dx. Yeah, a over pi. Okay. So you putting it all together, you can see that, you know, this is root a over pi e to the minus ax squared, limit a going to infinity. Okay. So there are many other realizations of the delta function. I mean, the dumbest realization you could imagine is just a box whose width is, you know, L and whose height is 1 over L. Right? So you would write this as L limit L going to 0, in this case, 1 over L times a step function. Let's say if the box is this is the origin, then this would be a step function of x step, what is it, or minus x, something like this. Check that. That's another example of a delta function. And let's see. So the example that's relevant here is that the sum e to the 2 pi I, we'll use a different thing, phi n equals 0 to infinity, or minus infinity to infinity. Actually, let me put an n max here, n minus 1, right? So this is a geometric series, right? Do you remember how to do geometric series? So let me write it out, 2 pi I. Sorry, that's the term, running out the clock. I don't think I'm gonna start the next part of the notes, so I may as well just make you guys slightly more comfortable with these manipulations. Sorry. 4 pi I5 plus e to the, 6 pi I5 question mark. So how do you do geometric series? Pop quiz. I don't know, when do people learn geometric series? Sorry, you can't see my face, but that's okay.
I think it was Calc 2.
Good, okay. Let's see if you remember how to remember your Calc 2.
It was a formula. I don't remember the formula.
Well, how do you do it? So, right, so I think it's the magic of recursion, right? Right, so whatever the answer is, so let's call it the answer.
You're sharing your screen, right?
Oh, am I? Crap, okay, I apologize. Do you see my screen now?
Yeah, I can see it.
I can see it.
All right, so let's call this, I don't know, what letter should we use? G, for geometric. So what you see is that if you pull out one of these factors and regroup the rest, this is G. And so this is an equation for G. G is equal to G. So you can see that G from this is 1 over 1 minus e to the 2 pi I5. Okay. And so what you see now is that this function is funny. When phi goes to be an integer, what happens to this function? Blows up, right? This function is also complex. So the thing that we want to look at is the square of this function, because that will have that could in principle have an interpretation as a probability, and this function will look like all right. So I think the punchline here is that with a little bit of extra work, you can convince yourself that this object, the square of this object, the absolute value of the square of this object behaves like another delta function. Okay, where, sorry, let me just write this out correctly. Minus m, where m is in integers. Okay. All right. Let me see if there's anything that's simple that I can tell you from the rest of this. No, I think I'd much rather just narrate the rest of it and post it on YouTube. Okay, so did anybody respond to this invitation to do homeworks?
Yeah, I put some times in there.
Okay, good. So I'll respond to that, and let's try to I'll try to find something. Okay.
Okay, thanks, Professor.
All right. Take care.
You too.
right.
Unfortunately, I can't do any day. I can't do Wednesday because I'm actually flying down to North Carolina. But Monday,
Well,
Tuesday.
whatever. We'll record. Whatever we do during this homework solving session, I'll record it and I'll post it on YouTube as well.
Okay, thank you.
All right. Bye.